So we will start within 5 minutes. Let the other students join. We will take the remaining part, that is the design of counterfort. So design of counterfort. Now design of counterfort. This is last design in this numerical. So from the last 4 lectures we are solving this numerical. Now this is the last part. So to design the counterfort, first we need to find out the inclination of the counterfort with the horizontal. So now if I draw the diagram of the counterfort in our case, so it is like this. This is the height of the counterfort. Then this is the 2.7 meter distance hill slab, and then here is the counterfort in this way. So this you have already known the dimensions. So this dimension it is 6.4 meter, which is height. This dimension is 2.7 meter. So this is 6.4 meter. This is 2.7 meter. Now the maximum depth it can have is this one. This will be the maximum depth it can have, and let us say that this depth is d dash. This angle is 90 degree as we drop the perpendicular. So now you can see this is the inclination angle theta of this counterfort. Inclination angle theta. Now I will write here inclination of counterfort, inclination of counterfort with horizontal. So that we are going to calculate. We consider this triangle, this right angle triangle. So in this right angle triangle, if I use tan of theta, then it will be opposite side. Okay, opposite side upon Instead of tan of theta, if I go for sine of theta, because this side is known to me, this is the hypotenuse. So instead of tan, if I go for sine of theta, then it will be equal to opposite side, that is d dash, divided by hypotenuse. Hypotenuse is 2.7. Hypotenuse is 2.7. Okay. So this is the inclination of this counterfort with horizontal. But now, if I consider this big triangle, here I will give the name. Suppose now this is A, B, C, and D. Okay. So this is from triangle DBC. This is from triangle DBC. And then again, if I use tan of theta in this big triangle ABC, now if you consider the ABC, this angle is 90 degree. So here tan of theta is equal to opposite side 6.4 divided by adjacent side 2.7. This is from triangle ABC. Simple trigonometry is there, simple geometry is there. So now from this we can find out the theta. So therefore theta is equal to tan inverse of 6.4 by 2.7. This is the value of theta. So therefore we can calculate the theta, and this the value of theta, which works out to be it is something 67 degree. Okay, 67 degree. So if you calculate, I will calculate that value now. 6.4 divided by 2.7. So shift, then tan inverse of answer, it is 67.12. So it is 67.12 degrees. So this is the value of theta. Now if we keep this value in this equation, whatever we have got over here, so that we will get the value of d dash. So here, now I will put that value. So therefore d dash is equal to, it is 2.7 into sine of 67.12 degree. So which is equal to, this comes out to be 2.487 meter, which is nothing but 2487 mm. So this is 2487 mm. Now the maximum moment, is equal to, so how do we calculate the moment? So the lateral pressure, which is nothing but half into Ka into gamma into h is the height. Okay, into its CG will be at a distance of h by 3 into L, where L is this L is nothing but it is the spacing of counterfort. This is the spacing of counterfort. So this is the spacing of counterfort. Now if we put the values, then M is equal to, it is 1 by 2 into K is 1 by 3 into gamma is 18 into height is 6.4, h into h cube I will write here, 6.4 into L is the spacing, it is 3 divided by 3. Therefore M is equal to, after solving this, you will get the value of M as 786.43 kilonewton meter. Now ultimate moment, further if we calculate ultimate moment mu is equal to, so the ultimate moment mu is equal to 1.5 into 786.43. To calculate this, let me know the answer of this value. Let me know the answer. I will wait. So the answer is 1179.64 kilonewton meter. So this is the moment which we have got right now. Now calculate the reinforcement. Now we are going to calculate the reinforcement. So that reinforcement is AST is equal to 0.5 FCKBD divided by FY in bracket 1 minus square root of 1 minus 4.6 mu upon FCKBD square. Therefore, AST is equal to, it is 0.5 into 20 into B is 300, that is the width of this counterfort, into depth right now we have calculated it 2487 whole divided by FY. FY is 415. Here in the bracket 1 minus square root 1 minus 4.6 into 1179.64 into 10 to the power 6 divided by FCK B D square. Bracket close. So therefore AST is equal to, solve this and let me know the answer. Do the calculation, solve this equation, let me know the value of AST. What is the answer? After solving this, the answer is 1366.30 mm square. This is the answer. Now take the check for the minimum steel for this. So as per IS 456-2000, clause number 26.5.1.1, page 47. Page 47. AST minimum for this type of structure, it is 0.85 BD, you can refer the IS code, divided by F1, which is equal to 0.85 into B is 300 into D is 2487 divided by 415. Therefore, AST minimum is equal to, calculate this now, AST minimum. So the answer is 1528.15 mm square. So provide the minimum steel. Okay, provide the minimum steel. So now calculate the number of bars for this steel. So here I can write AST is less than AST minimum hence provide reinforcement according to AST minimum So therefore calculate the number of bars now. So I will use 25 mm bar diameter. Use 25 mm diameter bars. Now if I use 25 mm diameter bars, the number of bars is equal to, what is the area? 1528.15. So it is 1528.15 divided by area of single bar 5 by 4 into 25 square. Now calculate this. 1528.15 divided by area of single bar. It is 3.11, which is nearly equal to 4 numbers. So here I will write provide 4 bars of 25 mm diameter in flange of counterfort. Okay, flange means that flat portion, that is called as flange. So in the topmost portion of the flange, that flat inclined portion, where we are going to provide these bars. So now next is the vertical ties. Next is the design of vertical ties. We are going to provide vertical ties. So for vertical ties, consider 1 meter height, 1 meter height of counterfort. Consider 1 meter height of the counterfort. Maximum pressure on stem. This we have already calculated. Still, I will calculate once again. Ka into gamma into h, that is the height of stem, which is equal to 1/3 into 18 into 6.4, which is equal to 38.4 kilonewton per meter square. The maximum force on counterfort. It is equal to this intensity 38.4 into length. Okay, into height we have considered 1 meter. So into 1, if you do it, then this is how much it is. I will calculate now. So it is 38.4 into 2.7. It is 103.68. 103.68 kilonewton. So this is the maximum force. So now factored force. So the ultimate force is equal to 1.5 into 103.68, which is equal to it is 155.52 kilonewton. So now we know that for the TU is equal to, we have studied this in DCS1, tensile force TU is equal to 0.87 Fy into AST. From this also we can calculate the area of steel. So that is the force is 155.52 into 10 raised to 3, which is equal to 0.87 into Fy 415 into AST as it is. So therefore, AST is equal to, so what will be the value of AST? It is 155.52 divided by this 430.74. This value is 430.74 mm square. Okay. Then spacing. Then spacing. So first of all, calculate the number of bars. So provide 8 mm diameter bar. Okay. Or 12 mm diameter bar. We will provide 12 mm diameter bar. So use 12 mm diameter bar. Therefore, number of bars is equal to 430.74 divided by 5 by 4 into 12 square. 12 square. So it is 430.74 divided by 5 by 4 into 12 square. So it is 3.8. 3.8. So which is rounded up to 4 numbers. Which is rounded up to 4 numbers. Now AST provided. Calculate the AST provided. So what we are going to provide? We are going to provide 4 bars and each of bar diameter 12. So here it is, what is the AST provided? It is 452.38 mm square. Now calculate the spacing. As we have considered the 1 meter already height, so we will calculate the spacing. So the spacing S is equal to AST provided area of single bar divided by AST provided into 1000, which is equal to. So now we will calculate the spacing. So it is 250 mm center to center. So provide 12 mm diameter bars about 250 mm center to center. So this is about the vertical ties. Now this is vertical ties we have provided, that is the vertical bars. Vertical reinforcement is over. Now we will look for the horizontal ties. Okay. So next is the horizontal ties. So horizontal reinforcement in counterfort. Now we are studying only the counterfort. This steel whatever we are providing, it is for the counterfort. So that counterfort is, it is in triangular shape. So in that counterfort we have designed now vertical bars. Now we are designing the horizontal bars. So we have already calculated the maximum pressure on the heel slab. So maximum pressure on heel slab at bottom we have already calculated, it is 77.94 kilonewton per meter square. Okay. So the maximum force on counterfort. This calculation we have already done. You can refer the notes. Okay. While designing the heel slab, we have done it already. So now maximum force on the counterfort. It is how much? It is 77.94 into what is the length? It is 2.7. So it works out to be, I will do the calculation, 77.94 into 2.7. So it is 210.43. 210.43 kilonewton. Okay. So ultimate force is equal to 1.5 into 210.43. So if you multiply this by 1.5, then ultimate force will be 315.64 kilonewton. So this is the ultimate force. So now we will calculate the AST. We know when the force is given, then TU is equal to 0.87 Fy into AST. You can use CU is equal to, also you can use the formula, but in that XU max, that everything is required, so we need to calculate that. So therefore we have avoided this. Okay. And why we use this formula TU and TU into 0.87 FYST? Here we have we have not calculated the bending moment for this vertical ties and horizontal ties. We are designing the steel directly from the force. This formula helps you to calculate the steel directly from the force. T is nothing but it is force. Okay. And that AST formula, in that the moment value is required. Here we have not calculated the moment. So that is why by using the force and by using this equation, we are going to calculate the area of the steel. So now here the area of the steel, if I want to calculate, now the TU, it is 315.64 into 10 raised to 3, which is equal to 0.87 into Fy 415 into AST as it is. Therefore, AST is equal to 315.64 E3, 315.64 kilonewton, 0.87 into 415. So it is 874.22. So this value is 874.24 mm square. So now again use 12 mm diameter bars. 12 mm diameter bars. So therefore Therefore, S is equal to, now not S, we will calculate number of bars first. Number of bars equal to area of steel divided by area of single bar. It will be it will be 7.72, which is rounded up to 8 numbers. So calculate now AST provided. So provided AST provided is equal to 8 number of bars. Each of bar diameter is 12. So do the calculation for this. It is 904.77. 904.77 mm square. So this is the AST provided. Now calculate the spacing. Spacing S is equal to, so the spacing S is equal to area of single bar. So here I will erase this. On the next board we will take this. So spacing S is equal to, spacing S is equal to, so it is AS area of single bar divided by AST provided. Nine zero four point 77 into width, that is 1000. So calculate this value and let me know the answer. One 125 mm. Okay. So the spacing is 125 mm, center to center. So finally you can write over here, provide 12 mm diameter bars about 125 mm center to center. Okay. Provide 12 mm diameter bars about 125 mm center to center. So provide 12 mm diameter bars about 125 mm center to center. Now we will draw the reinforcement details. The previous data is not with me when we have started this problem. So you should have to tell me the number of bar diameter and spacing. You have to check whether I am writing it correctly. I will tell you which bar is of which. So now here first we will draw the diagram. So I will draw the retaining wall. we are going to show the reinforcement details in the retaining wall. So here is the shear key. This below portion increased depth we have put for the shear kit is 300 mm. We have given this for the shear. So now we know the dimensions already. So we will directly go to the reinforcement details. So the first bar, that is the main bar in the stem, and it will start from this end. Then it will move down. It will move down up to the shear key. Okay, it is continued in the shear key, and then it will bend again. From here, it will bend again over here, somewhere here. This is the main steel bar in the stem. The another main steel bar in the stem, it will start from this point, then it will come here, into the stem, and then it will bend. From this point, it will again bend into the shear key. This is the main steel of the stem. This is the main steel of the stem. So for main steel, I'm not remembering what design we have done, but 12 bars. About what was the spacing for the main steel? Main steel reinforcement सांगा मला ह्याची स्टेमची. What was the main steel reinforcement of the stem? We have already designed the stem. Let me know the main steel reinforcement of the stem. Okay. In between, I will draw the distribution steel. You tell me the value of that. What we can say, main steel. 12 bars, about 100 center to center. Okay. So this is the main steel. So these bars, these are 12 diameter, about 100 center to center. Now we will give the distribution steel in the stem. So these are the distribution steel bars. Let me know in the chat what distribution steel we have provided for the stem. Let me know the value. So what is the value? It is 12 bars, about 200 center to center. Okay. So these are 12 mm bars about 200 mm center to center. So now, what is the this what we can say main steel in hill slab? Let me know the main steel in the hill slab. That bar I am going to draw here right now. The main steel in the hill slab. So what is the main steel in the hill slab? Let me know what is the main steel in hill slab. Sixteen mm about 200 mm center to center. So this is your 16 mm diameter bar about 200 mm center to center. And then I will draw the main reinforcement bar for toe slab. It will start from here, this point. Then it will move further. It will start from somewhere here. Now from here it will move further. Come like this. This is the main steel in toe slab. So what is the main steel in toe slab? Main steel in toe slab. In between I will draw the distribution steel. This is the distribution steel. 16 mm diameter about 160 mm center to center. Okay. So this is 16 mm meter about 160 mm center to center. Now let me know what is the distribution steel. Distribution steel in hill slab. 12 mm bar about 250 mm center to center. So this is 12 mm about 250 mm center to center. So this is the reinforcement. I will draw the distribution steel here on this side also. Side also. Okay. So this is in this way here the steel is provided. If you give the dimensions now, so the dimensions are this dimension it is 300, this is 6.4, This is 0.3. This is also 0.3. Okay, so I will write over here. This is 0.3 meters. This is 6.4 meters. This is 0.3 meters. This is 300 mm. This is the shear key. Okay. So we have designed it for 300 mm. We have provided the depth as a 300 mm. This is 300 mm. That is 0.3 meters again. Okay. So we have provided that much of the depth. So this is the reinforcing details in the counterfort retaining wall. Now we will show the reinforcement detail in counterfort also. Now counterfort will be there. Here you can see if you join from here to here, the counterfort will be there. But in this section, it is difficult to show the steel of the counterfort. It will not be visible in this section. Okay, separate section of the counterfort we will take, and in that counterfort I will show you the design. So here, now I will draw the counterfort. This is the counterfort section I am drawing. Okay, so here in this counterfort now, the reinforcement is very simple to show. I will show the vertical reinforcement first. So all these are the vertical reinforcement bars. With definite spacing. Just now we have designed vertical ties. Those vertical ties I am showing over here. This is the vertical ties. So what was the diameter of, what is the spacing and all these things for this vertical ties? Just now we have done now for vertical ties, where it is 12 bars about 250 center to center. So these are 12 bars about 250 center to center. Now similarly, we will draw for the horizontal ties. So these are the horizontal ties. The length of the steel bars will vary according to the length available or the length of this counterfort. So here it is 12 bar about what is the horizontal ties? For horizontal ties 125 center to center. So about 125 center to center. Okay. 125 center to center. And this is the reinforcement. This is the bar in here. This bar which I have shown. This is not the design. This is the bar which I have shown. So here the topmost bars. These are nothing but these are the 4 bars of 25 mm. which we have provided in the flange. Okay, which we have provided in the flange. So if we see the 3D of this, it will be like this. No, it will be like this, and this flange will be there. Flange will be there, and in the flange, these bars 1, 2, 3, 4. These bars 1, 2, 3, 4. In this way, the same cross section of this cross section will be on that side also. Okay, I hope now you are imagining the things. Okay, so the same cross section will be on that side also, and these 4 bars here we can show that those 4 bars, or instead of showing here, you can show in the what we can say top plan also. In the top also, when you see that counterfort from top view, if you take the top view, then also you will see those 4 bars for this counterfort. Okay, so this is the design. Still, if I show you this in the detail, then what I will do, just 1 minute, I will show you all the bars. Okay, so just I will take it below. Now here you can see the perfectly horizontal, no, perfectly horizontal, like this. And now I will join this. Okay. So in 3D now I am trying to show you how those 25 mm bars will be there. So from this point, we'll move down. This is I am drawing the counterfort, and it will be like this. And on that side also the similar cross section will be there. On that side also, this if I show you in dotted, then this will be like this. This will be the perpendicular, and these 2 points will join points, okay, from in this way, from this side also, and it is joined over here like this. Okay, so this is your counterfort. This is a counterfort structure, and in this counterfort now we have provided these 4 bars. So first of all, these bars I will show you what I have erased. So here this is the bar which is vertical ties. So vertical ties, what was the dimension for the vertical ties? For the vertical ties, 250 mm, and for horizontal ties, okay, so net was got disconnected. So I will tell you that detailed reinforcement of counterfort once again in by drawing the diagram. So this understanding of the reinforcement is very important. Design, anybody can do the design, but the reinforcement understanding should be there. So here, this is the counterfort this way. This is the counterfort. This is the cross section of the counterfort. You will see. Now, if I draw, if I extend it like this, then it will look like in this fashion. Okay. I'm trying to draw it correctly, and I will show the behind section this by the dotted line. Okay. Here It is like this. And now this is the 3D. Okay. So this type of diagram will be there. And now our reinforcement, we can show the vertical ties and horizontal ties. Now these are my vertical ties. This we can show over here in this reinforcement. On that side also the same thing will be there. Okay, here the vertical ties will be there. And these vertical ties are, and these are of, this is 12 mm about 250 mm center to center. The second thing is horizontal ties. Those are provided like this. This is the provision of horizontal ties. It is though these horizontal ties are closely spaced. 125 mm center to center spacing is there. I have not shown here properly, but still you can understand. So this is nothing but 12 mm diameter about 125 mm center to center. And now the bars in the flange, those bars, okay, those are bars like this. These are the bars like this. So 1, 2, 3, and this is the fourth one. Okay. And these red bars, अरे shear key तर काढली की मागच गेली की shear key you will see the shear key in the what we can say retaining wall cross section. This is the cross section of counterfort. So where is the question of shear key in the counterfort? Shear key is provided in the counterfort retaining wall. So in the cross section of the retaining wall, you will see the shear key bottom below the base slab. Shear key is provided. Shear key is not provided in the counterfort. I am not showing the section of retaining wall. This is the section of counterfort. Okay, please be clear with this. One question is there. Where is the shear key? So this is the section of counterfort only. हे जे तुम्ही एवढं सेक्शन बघत होता ना तोच एनलार्ज करून दाखवलाय मी. दिस इज द सेक्शन ऑफ दिस मच ओनली काउंटरफोर्ट. This is counterfort. This is not the section. This section I have shown over here. This is your counterfort. This height is 6.4 meter. This is 2.7 meter. So that I am showing over here. Counterfort. Okay. This is not the section of this retaining wall. So here there will not be any shear key will be shown over here. Shear key will be shown in the last diagram, reinforcement diagram. Before this, whatever we have drawn, in that I have also given the dimensions of the shear key. Please pay the attention. So now here these bars will move forward like this. In 3D I am showing to you. These bars will go like this. Okay. It will move like this one. And these bars which were provided over here, this will move in this direction. So this I have tried to explain you how the counterfort steel is placed. So in this way the steel is placed. Okay. This way the steel is placed so in the counterfort retaining wall. So these bars These bars are nothing but these bars are 4 bars of 25 mm. So now hope you understood the section of counterfort. This is the only section of the counterfort. Previous to this, I have already drawn the section of the retaining wall. In that, we have also shown the shear key. In that, we have shown the stem bars and all those things. So this is the proper design of retaining wall. So in this way, we are going to design the retaining wall. So we have seen the design of cantilever retaining wall, also the design of counterfort retaining wall. So with this, this unit is over. Okay, there is no much variety. Just two types of retaining walls are there. Those two types of walls we have covered over here. These walls. So now the next topic is the design of water tank will be there. That we will take. So design of water tank, hardly it will take 1 hour. We will see the procedure of GSR, and that's it. The GSR is only required. Okay. Other two procedures, if you want in detail, then you should call me or personally meet me or online personally. I will tell you how to design, because the counter, it is much more lengthier than the 5 times of this counterfort retaining wall. Okay, counterfort retaining wall. So those questions will not be asked in the examination. And then we will see the design of the GSR, and then our syllabus will be over. Then I will drop the links of the MCQ. Already I have updated everything in the teaching diary. Please go to the teaching diary. There in the teaching diary, see that assignment. I have given you the assignment also. Assignment booklet is also attached. So unit wise assignments you need to solve. So solve those assignments also. I will share you the link where to upload the assignments. At that link you have to upload those assignments. Okay. So now I think we will take the break of 5 minutes. Okay. And then we will start with the water tank. We will design the water tank. I will tell you the steps how to design the water tank. Just remember those steps for the GSR, and because it is by working stress method. Okay. And the thing is that you have not studied the working stress method. You have studied all the design by limit state method. Now you can say it is the syllabus is set in that way or any other thing, but the water tank is always designed by the working stress method. So some formulas are there in the working stress method, like the limit state method. So those formulas I am going to tell you directly. You have to just put the values in that formula, and you will get the answer. Okay. So now 140 time is there. So at 145 now, we will start it once again, the design of water tanks. Okay. Instead of 145, 150. At 150, we will start the design of water tank. Okay. So I will keep on this link, and we will start after some time. Okay. At 150, we will start. So now we will go for the next thing, that is water tank. So as I have told you earlier, only the GSR circular water tanks with flexible base that we are going to see. See, in the water tank, there are basically two types. Flexible base water tank and rigid base water tank. So rigid base water tank is not there for your syllabus. It is at higher level MEM Tech. Actually, the design of water tank is made. It is done by using the softwares. Okay, it is easier to do the design on the software, that is the analysis part. Only the steel is manually provided for the water tanks, and the manual procedure is little bit cumbersome for the underground storage reservoir, then elevated storage reservoir. Okay, so from the examination point of view, if the offline examination is there, then only GSR is asked for the examination, ground storage reservoir. That too, the circular tank is asked. Again, in the rectangular tank, the design is again quite what we can say, quite lengthy, and for that the base of working stress method is also required. Okay. So in the limit state method, we take that modular ratio M as the ES upon EC, but in the working state that value nearly comes out to be equal to 6 or 20 something. 20 value will be there, but in the working stress method, that same M value we are going to take it 13.33 value. So in the IS 456 2000, now in the latest IS code in the 2000, this um, many of the working stress methods are removed in this revision version. So you have not come across some formulas will be there which you have not came across of those formulas. Okay. So that formula you have to remember that, and you have to do it like that only. Okay. So, but as your examination is, I think, online now, so I will provide you the MCQs and all those things. I have already uploaded. Now, if you see the teaching diary of this, what we can say, DCS2 subject, from your description link is there. Then I have already uploaded the MCQs, also the chapter notes, and then assignments. Everything is uploaded over there along with the video lectures. So you now start your work, and after this, now today we will finish this design, and after this, now in the next lecture, now I will take the practice problems for the prestressed concrete design, that stress concept, strength concept, the new variety of the problem. We have covered everything, but still some, if the some little bit modification is there in the numerical, still I found that while teaching to the previous batches who have given the offline examination, it will be difficult for them to solve that problem. So those types of problems after this lecture also we are going to take. So now today is the, as per the official syllabus, so this is our last design of the water tank that we are going to see now. Okay. So here first of all I will write what is the meaning of water tank. So in short, so water tank, so a reinforced concrete tank, and also on the competitive examination there, water tank, on the water tank questions will not be there. Okay, one or two question you will find on the water tank. So weightage also in the competitive examination also it carries a less weightage. Okay. It is very useful in a reinforced concrete water tank, is very useful structure which is meant for the storage of water. Storage of water. Okay. So water tank, generally, you know what is water tank. So I'm not going into the explaining what is water tank. But in the water tank, you should know this thing, that water tank basically it is rectangular or circular we will consider it as a base slab on which the wall is resting. In that way, we are going to design the water tank. Means suppose this is the base slab, and on this base slab, this side wall is resting, this side wall is resting. In this way, we are going to design the water tank. Whether its cross section is rectangular or circular, it doesn't matter. So now just some standard values of stresses are there. So those standard values, I will tell you. You have to remember these values. These values, it is not given in the IS code. These values given, but one or two, three values are given. All the values are not given. So you have to remember these values. The stresses in the reinforcement. What are the stresses in the reinforcement? Those we are going to see over here. First, we have to make the table. In first column, reinforcement. First column, I will write reinforcement. So in the second column, permissible tensile stress in the reinforcement. This is the second column. Again, second column is divided into two categories. That is, first is the net water phase. Okay, net water phase. And second column is away from water phase. Away from water phase. So at the water phase, what is the permissible stress, tensile stress, and away from the water phase, what is the permissible tensile stress? That value, standard values are there that I am going to give you. So for the FE 250, so for FE 250, it is 115, okay, Newton per mm square. At net water phase, and away it is 125 Newton, 125 Newton per mm. So this is for Fe250. Then Fe415, it is 150 Newton per mm square at net water phase. Away from water phase, it is 150 Newton per mm square. Same thing. When the thickness of wall of water tank, and the thickness of member is less than 225 mm. When the thickness is less than 225 mm, and it is 190 Newton per mm square when the thickness is greater than 225 mm. That in the case of 415, we have to pay attention at this. Then Fe500. In the case of Fe500 here, it is at net water phase 205 Newton per mm square, and away water phase 245. Okay. So in the hydraulics, you have already studied what is towards water phase, at the water phase, and away from the water phase. Okay, so these are the tensile stresses which are getting developed for the different grades of the steel: 250, 500, 415, and 500. And these are the values. These values you should remember. Again, I am telling you, these values you should remember these values. Okay. Now we will take one GSR example for this. So design a circular tank resting on firm ground, to the following. First, diameter of tank diameter of tank, which is equal to 3.5 meter. Second, depth of water, which is equal to 3 meter. Third, the wall and base are not monolithic, with each other. Okay. So if the base slab of the water tank and wall of the water tank are casted together, that is, if the monolithic construction is there, then it is called as the water tank with rigid base. And if the base slab is constructed separately, after that the walls are constructed, those two are the not monolithic, so that those are called as the water tank with flexible base. So the next thing is specific weight. Also, this is the easiest procedure which I am telling you right now to design of the water tank. Okay, so in the book also you will get a very lengthy procedure for this also. So it is better you write it down, take the screenshot as well as write it down. Okay, it is better for you because you have to remember this, because likewise in the limit state method you are having some base, you know something. Okay, but this working stress method is totally new for the you, and only one design is there in this working stress method, so you have to remember this. So write down neatly and you have to remember this, how to design. So the specific weight of water is equal to 9810 Newton per meter cube. Okay. Use M25 and Fe415 steel. So we are going to use M25 and Fe415 steel. So we need to design this water tank. Okay. So the first step in designing the water tank is finalizing the thickness of the wall. What will be the thickness of the wall of the water tank? That we need to first finalize. So first is thickness of wall. So to finalize the thickness of wall, there are two criteria to finalize the thickness of wall. First is, and the greater of two we should adopt. Greater value of these two we should adopt. So first is 150 mm. Thickness of wall is 150 mm. I will write here. The wall may not be less than. It should not be less than. First 150 mm, first criteria, and second is 30 mm per meter depth. 30 mm per meter depth plus 50 mm. Plus 50 mm means what? 30 mm per meter depth. Now what is the depth of the water tank? Here it is 3 meter. So per meter means for 1 meter. So for 1 meter we have to consider 30 mm. So for 3 meter it is 90 mm. Okay, so I will do here the calculation. You can see now 30 mm per meter. So for 1 meter 30 mm, for 3 meter 3 into 30 plus 50 mm plus 50. So it works out to be 140 mm. That is 140 mm. So greatest is 150 mm. So here I will write provide thickness of 150 mm. So we have provided the thickness of 150 mm to the wall. Okay, so this is your step number 1. What you have done, you have finalized the thickness of the wall. Okay, you have finalized the thickness of the wall. After the thickness now, consider consider the bottom 1 meter height of the wall, pressure intensity corresponding to the center of the bottom 1 meter height wall. 1 meter height of wall. So what we are doing now, see our total depth is 3.5 meter. Total depth is 3.5 meter. So we have choose a point, we have choose a section from 1 meter from the bottom. From bottom 1 meter. Total is 3.5. From bottom we have taken 1 meter. Okay, and at that point now we are analyzing what are the hoop stress and all those things, because at that point it is maximum. So here we will calculate the stress now. So the stress is equal to, you know the formula, it is rho into H. In hydraulics you have studied the formula. Due to the water pressure, a static water pressure, it is rho into H, where rho is the density of water, H is the height where it is stored, that height H, and rho is the density. So rho into H is the water pressure that we consider. So here I will write W into H. So it is 9810 into 2.5. Total height is 3.5, but we are considering at 1 meter from the bottom, that where we have taken the section. So 3.5 minus 1, what is remaining? It is 2.5 meter it is remaining. So that we have considered over here. And if you do the calculation now, it is 9810 multiplied by 2.5. So it works out to be 24525. Okay. So it is 24525. So 24525 Newton per meter square. Okay. Newton per meter square. Now, due to this water pressure, hook tension is getting generated over there. Hook tension is there. So that hook tension we need to calculate. So hook tension you might have studied in the SOM, thick and thin cylinders. You have might have studied in the SOM thick and thin cylinders. In thick and thin cylinders, you calculate this hook tension. Okay, for thin cylinder, for thick cylinder. So that formula we are going to use over here. So hook tension. So hook tension T is equal to, the formula will be stress into diameter divided by stress into depth divided by 2, because this is the depth we should take. So it is, the stress is 24525 into our total depth is now 3.5 divided by 2. So if you do this, what is the answer? Do this calculation. It is 42919 Newton. Okay, 42919 Newton. That is the answer. Now steel required is equal to, that is, I can take over here, the steel is nothing but area of the steel we need to find out. So area of steel is nothing but, it is the force. Okay, it is the force divided by stress. This is the basic formula to calculate the area. So force, it is 42919 divided by stress, it is 115. Stress is 115. So if you do this, you will get the area, and that area is 373.2 2 mm square. This is the area. This is the steel required. This much of steel is required. Now minimum steel required. So we have to check that whether it is greater than minimum steel or less than minimum steel. So minimum steel required is equal to, it is the 0.3% of gross area. Also remember this thing. Minimum steel for this water tank wall, we have to take it as a 0.3% of gross area. So it is 0.3% of gross area, 0.3 by 100 into this area, that is thickness of wall we should consider. It is 150 into, we have taken the height, it is 1 meter. So 150 into 1 will be there. So here, if you do this calculation, what is the answer? 0.3 into divided by 100 into 150. So 1 meter माझ्याकडनं राहिलं की तुमच्याकडनं पण राहतंय. Here the thickness of wall is 150 and here we have taken the height as 1 meter. So 1 meter means into 1000. 1 meter means into 1000. Do that. Let me know the answer. $450. Okay. This is 450. Now see, the minimum steel requirement is 450 mm. Okay, minimum steel we should provide, that is 450 mm, and steel requirement is 374, near about 373.2. Okay, so we will go with the minimum steel. So we will go with the minimum steel because minimum steel is greater. So now bar diameter we will use 10 mm diameter bars. So if I use 10 mm diameter bars, then calculate the number of bars. So the number of bars is equal to, it is 450 divided by 5 by 4 into 10 square. To calculate the number of bars, it is 5.7, so which is nearly equal to 6 numbers. 6 number of bars are required. So calculate the AST provided. AST provided is equal to 6 bars we are going to provide, each of bar diameter 10. So this AST provided will be 471.23 mm square. This is the AST provided. Now calculate the spacing. So the spacing S is equal to, that is 5 by 4 into 10 square divided by 471.23 into 1000, that is the width, which is equal to 166.66 mm center to center, which we will round it up to 160 mm center to center. Okay, so this steel is required to place at, provide at both the faces. Okay, because two faces are there now. So this steel is need to provide at both faces, at both faces. So provide steel at each face, equal to 10 mm bar about 160 mm center to center. So this is the steel which we have provided. Okay, so this is the steel which we have provided 10 diameter bars about this 160 center to center. So our AST provided is 471.23 right now. But actually, if we see now, we have reduced here the spacing. For 471, we have got 166. But now our actual spacing is 160. So what is our actual AST provided? Actual AST provided. Now see, we have to reshuffle the formula. How do we reshuffle? We know that spacing S is equal to what? Area of single bar. So area of the bar diameter is known to us. Divided by here is the term of AST provided. And multiplied by 1000. So now in this case, what is our spacing? When you consider the area of 471.23, it is 166, but now it comes 160. So if I put over here the spacing is 160, then it is pi by 4 into 10 square, and this is my actual AST provided. This is required. In limit state method, this is not required to calculate in this way. Actual AST provided, it is not required over there, because there we consider the lot of factor of safety, but in the working stress method, factor of safety is not that much. That is why we have calculated actual exact area what we are doing. So here the AST provided will be as it is and multiplied by 1000. So now if you reshuffle the terms, you will get actual AST provided. We will get the value of actual AST provided, and it is 490. How much? 490.87 square. 490.87 square. Now why we have calculated this? Because it is required in further formula. So the next thing is tensile stress in concrete. So tensile stress in concrete is T divided by A plus, this is the formula, remember it, M minus 1 into AST, which is equal to, now this is the formula, so you have to remember this formula, which is equal to, it is 42919 divided by area is 1000 into 150 thickness plus M is 13.33 minus 1, this I have already told you, and into AST is 490.87. 490.87. So if you solve this, then you will get the tensile stress in concrete. Tensile stress in concrete, and if you solve this, that is this 491 divided by 150 into 13.9, so you will get the answer as 0.275 Newton per square. Okay, so this is the tensile stress. Now this tensile stress is 0.275, which is within the permissible limit. Okay, because if you see even limit state table, it will start from 0.28. So it is then still less than that also. So vertical distribution steel. So the vertical distribution steel, this is provided, this shall be at least 0.3% of gross area. 0.3% of gross area. So which is equal to 0.3 divided by 100 into 150 into 1000. So this value, so you solving it, you will get it as 150 mm square. 150 mm square. Okay, so it is very less. 150 mm square is very less. So still we will provide 10 mm diameter bar. So if you provide 10 mm diameter bar, calculate the number of bars. Calculate the number of bars. 10 mm diameter bar if you provide, use 10 mm bar diameter, then number of bars is equal to 150 divided by 5 by 4 into 10 square. So how many number of bars required? 150 divided by it is 1.9, which is nearly equal to 2 numbers. 2 number of bars are required. Okay, so 2 number of bars if it is required, then what is the AST provided? AST provided AST provided is equal to 2 into 5 by 4 into 10 square. So it is into 10 square. It is 157.07 mm square. So now the spacing S is equal to, it is area of single bar divided by AST provided into width. So calculate this, area of single bar divided by into 1000. So it is 498.03 mm. So which we will round up it to 490 mm center to center. So I will write over here, provide 10 mm diameter bar about 490 mm center to center. So this is in wall. This distribution steel we have placed in the wall. Okay, vertical distribution steel which we have placed in the wall, and earlier steel was there, that is 10 mm bar about 160 mm center to center, that we have placed in the as a vertical main steel in the wall, and this is the distribution steel in the wall, vertical wall. Okay, now this vertical wall is supported on the base slab. So for that base slab, some standard design steel is there, that is always to be provided. So for the base slab, here, this will be of 150 mm thickness, 150 mm thickness with top mesh and bottom mesh of steel with 10 mm bar diameter about 250 mm center to center. So in the exam also, the base slab design is excluded. They will not, even though in the offline examination also the design of base slab is excluded. It is not asked to design the base slab. It is not there for you to design the base slab because some higher concepts are required over there. Okay. So this is the standard thing which we always provide, 10 mm bar about 250 mm center to center. Okay. So now after this, I will show you the reinforcement details, how it is look like over here. So I will draw first the vertical wall. This is the vertical wall of the water tank. Okay. Now I will draw the base slab. So the base slab will be this is the base slab, and the thickness of base slab is varies at this after some point. So here from this point, this thickness is varied. It is like this. Here we can show like this. So now the reinforcing bars, if I show the reinforcing bars, so the first bar will be it will be like this. Here it is in the vertical wall. This is the vertical steel, main vertical steel. These are the vertical bars. These are the vertical bars. This only provided in the wall. It will not anchored somewhere here. So they will anchored here itself like this. They will not anchored in their self also. So the reinforcement is provided like this. So this is your main steel bars. So these are the bars which is 10 mm diameter, about 160 mm center to center. This is your main steel bars. Then here the distribution steel is there. So these are your distribution steel bars. We have designed the distribution steel just now. It is 10 mm bar, about 490 mm center to center. So this is 10 mm bar. Okay, so this is 10 mm bar, about 490 mm center to center. This is the distribution steel. This is all about the wall. Now the base slab, it is 10 mm bar, which is at 250 mm center to center. So that bar I will show you here. So at top, it is like this at the top. At bottom also the same bar will be there. Here it will move parallelly. And then it is taken at the top. Then it will move over here. And then it is anchored at this point. Here also this at top bar is anchored. This is your main steel bar. So this bar you can see this is your 10 mm diameter bar, about 250 mm center to center. And also the distribution bars, if I show over here, these are the distribution bars. So the distribution steel bars. So these bars are again So these bars are again 10 mm diameter bars about 250 mm center to center. Okay. So this is the vertical wall and base slab design of the water tank. In that also for you only the vertical wall design is there. Okay, base slab and all those things are very much lengthy things are there. So this you need to prepare. Okay. So we have covered all the 9 units, all the 9 numericals in all the 9 units. Okay. We have taken also you visit to the teaching diary link. There I have added the MCQs. Now only the MCQ of I think this water tank is not added over there. So I will also add that. In addition to this, you visit the site Exam Veda. Okay. And then you visit the site Sand Foundry. Sand Foundry is the site. You visit that. Also India Bigs. So these three sites you visit, there you will get multiple MCQ questions, and these MCQ questions which I have sent to you right now through this teaching diary. So if you prepare this, it will be more than enough for you for your examination. There will not be any question out of this. Okay, so you have to prepare this, and in the next lecture now we will take some numericals for the practice. So officially here now we have covered all the units and our syllabus is over now. So I will take the your attendance first. So I will take the screenshot and then so just wait. I will take the screenshot. Today's date 2nd of January. Just 1 minute. Okay, now you can drop your roll numbers into the chat box. So now you can leave the